Next up in our exploration of space is actually looking at spectra, which falls in really nicely with a lot of the stuff we did about quantum physics at the end of last year. So that's the kind of things you probably want to go and have a review of, because this uses a lot of those ideas. Again, we're in a land where chemists are going to have some advantages here, so if you can remember any of your chemistry from GCSE, it's probably going to help you. Right, so first thing we're going to talk about is ionization. Just a bit of terminology. Hopefully you'll know that an ion is a charged atom, so it's either gained or lost electrons, so it will have a positive or negative charge. That's how they're formed, by adding or removing electrons. So, example here, I've got an atom. An incoming electron could knock one of the orbital electrons out, which then forms it into an ion. This is a way that we can make a positive ion. We can also cause ionization by nuclear radiations, so alpha, beta, gamma, by heating, if I just heat it up and give the electrons enough energy they can leave, or by passing electric currents through gases. All these are ways of causing ionization. The reason I'm talking about ionization is because we need to know something called ionization energy. The ionization energy is the energy required to move one electron from an atom, and it is most often expressed in electron volts. Give you a second while you're trying to remember what electron volts are. There is an equation from AS you might quite want to look up. It's to do with work and charge. Might get you to this. That's all I'll say. I expect you to go and look. The definition above is the first ionization energy. There are also second and third ionization energies, which would then be the energy required to move the second electron or the third electron. So that's ionization. The other thing we need to know about is something called excitation. Now, excitation is the promotion of electrons from lower to higher energy levels within an atom. So in this instance, I've got an atom, I've got an incoming electron again, it hits one of the orbital electrons, but instead of completely removing it, it simply elevates the electron to a higher shell, a shell that is further away, so a higher energy level. And that's just used some of the kinetic energy from that incoming electron to do that. So we would then describe this electron here as being in an excited state. Now, atoms have multiple excitation states, so there are multiple places I can move the electrons, and there are multiple electrons I could move, and they have different energies. So talking about energy levels inside of atoms, this is how we often represent them. Now, we can do these numbers a couple of different ways, and most often you'll find that these numbers are actually negative. So this would be 0, minus 2, minus 4, minus 6, minus 8, minus 10.4. The ionization energy is what we call 0, and the lowest energy down at the bottom here would be the ground state. So that's often minus a relatively large number. And this is how much energy is needed to remove electrons in electron volts, and the lines that go across here are possible energy levels where an electron could move to. It can't move somewhere where there's no line. It's like rungs on a ladder. It has to have a ladder rung to stand on. It can't just float in the middle. So, bit more explanation then. Electrons are bound because of electromagnetic attraction, which you should be getting pretty familiar with by now. Electrons prefer to occupy the nearest possible position to the nucleus, so they prefer to be on lower rungs, and the lowest rung that they can be on is called the ground state, and that's the lowest possible energy level for that electron. Only 2 electrons can exist in the lowest possible energy level at the same time. Further electrons have to occupy higher energy states. So if I had 3 electrons, I could have 2 at the ground state and 1 at this state up here, this energy level. As I was saying earlier, the energy levels are measured with respect to the ionization energy, which is assigned 0 electron volts. All other energy levels are therefore negative. So the ground state in this diagram is minus 10.4 electron volts. Energy levels above the ground state, but below the ionization level, are called excited states. And different types of atoms have different energy levels. So if I did this diagram for a hydrogen atom and compared it to a helium atom, these rungs would appear in different places. So, excitation is going up, de-excitation is coming back down. Excited states are typically very, very unstable, so electrons don't stay there long. They tend to want to go back down. Usually within 10 to the minus 6 of a second, the electron will drop back down to a lower energy level. And as it does that, because it's moved to a lower energy level, it has to give out some energy. And it's going to give out a specific chunk of energy that's equal to the difference in these energy levels, and it emits that as a photon. So, with each fallen energy level, a photon of electromagnetic radiation is emitted. Now, exactly what that photon is like is going to depend on how big the gap between the energy levels is. But the energy will be equal to the difference between the first energy level and the second energy level, and that energy is equal to HF. Like I said, we're calling back some of the bits from AS there. So that's H, which is Planck's constant, times the frequency of the light, and that gives you the energy of the photon. Okay, so let's just have a little look at some options we've got here. So if I wanted to excite a photon, excite an electron, I could do it using a photon. So what I could do is an incoming photon can be absorbed by an electron in the atom. It might not have enough for ionization, but it might have enough to cause excitation. Note, if it were to ionize it, that would be photoelectric emission, and we talked about the photoelectric effect last year. So you could imagine I've got a sheet of metal here, and I'm shining a light on it in order to try and move the electrons around. But if my photon doesn't have enough energy to completely remove an electron, it could simply excite it, so cause it to jump to a higher energy level. But that excitation can only happen if the incoming photon's energy is exactly equal to the difference between the two energy levels that the electron needs to move between. If it's too much, can't take it. Too little, can't take it. It's all or nothing, and it has to be exactly the right amount for this to happen. If it does happen, then that photon ceases to exist because its energy has been absorbed. So, let's look at some examples of fluorescence. So this is how things can give out light. So I could have here, this is my atom, I've got a ground state, then I've got these two excited states, which are 4.9 electron volts above the ground state, or 5.7 electron volts above the ground state. If I put in a 5.7 electron volt photon, it could cause an electron to be excited up to this higher energy state. What could then happen is that this photon can drop down to the 4.9 electron volt energy state, thus emitting a 0.8 electron volt photon. It can then drop again, emitting a second photon at 4.9 electron volts. Basically what I'm saying to you here is that the electrons can fall back down in steps. Now see what we did here. This is mind-blowing what I've just done, believe it or not. The thing we said about quantum physics and about photons is that they are smallest packets. I cannot divide them up. But look at what we've just done here. I've taken a 5.7 electron volt photon, absorbed it, and emitted two smaller photons. So basically I've taken one big photon and split it into two smaller ones. This is a mechanism that allows me to divide up the amount of energy inside a photon. That's pretty cool. I know you're sat thinking, yeah, so what? But it is pretty amazing. It's perfectly allowed because I completely absorb this 5.7 one, it's gone, and then we just emit two smaller ones. I mean, I'm not literally snipping the first one in half, but it has the same effect as doing that, which is actually very, very useful. So basically what I'm saying is that in this instance, the excited electron de-excites in two steps, which produce two photons. One was visible light, second would be UV, just at a slightly lower frequency than the original. So basically I've been able to take a substance which has absorbed UV and then emitted visible light. So these are basically examples of fluorescent chemicals, so things that can take in the bit of light we can't see, then emit light we can see. So it almost makes them seem brighter than they would be otherwise because they've taken the light we couldn't see, which is quite cool, where they're used in toothpaste and washing powder. So you probably sat there thinking, well, yes, okay, lovely, great. Why is this in the space topic? And it is because of these things here. I've got two spectra here. This one is called an emission spectra, and this one is an absorption spectra. So, if I were looking out into space and I saw some light coming from a star, I could analyse exactly what wavelengths of light were contained in it, and I might see these 5 bands. They are very specific wavelengths, and it just so happens they correspond to specific de-excitations inside an atom. So the differences between those very specific energy levels, they emit specific wavelengths of light, and I can spot them. And because they are very unique to the atoms, I can say, right, okay, that's from some H2. I know that that's coming from some hydrogen, so that must be hydrogen in that star. This one here is an absorption spectrum. So this would be where, say, I've got a continuous light source shining through, say, a gas cloud. And the gas cloud has absorbed specific wavelengths, because remember, I can only absorb photons that are exactly matched to the possible jumps for electrons, which is why they line up with the emission spectrum. So again, I could look at this absorption spectrum and go, right, that cloud must be filled with hydrogen gas. So this is how it links into the space stuff, because it lets me identify what is out there by looking at the spectra, whether they're emission or absorption spectra. Okay, and there we go. Next up, this is just another example of showing you how these lines line up. So this is the Balmer series from the hydrogen, and you can see how each of these transitions matches up to one of these lines that we can see. And they really are this clear and this easy to see. We'll have a look at some of these using some diffraction gratings, so we can do them for some specific atoms, and you'll be able to see the specific lines that they emit. It's really quite cool. Okay, that is it for this one. Remember, if you've got any questions, just ask me when you see me.